Good afternoon. In the last lecture, we introduced some concepts from estimation theory, and we showed how to estimate some hidden parameters based on some random or some uncertain data that we have, or we have some data with certain uncertainty, and it is important for the machine in order to extract some useful information about some parameters behind that data. And we showed a few examples, like if we have two outcomes, sorry, like success and fails, for example, and then we are interested to estimate what is the probability of success, and we showed how to find the maximum likelihood estimation. And also during the last lecture we introduced the difference between different criteria when we say maximum a posteriori or maximum likelihood or minimum least square or min-max criteria. So we introduced several criteria, and also we compared between them, and then we show when we should apply, for example, the maximum likelihood or the maximum a posteriori. And then we explain what is the concept of optimality here, when the maximum likelihood become optimum estimator or suboptimal estimator. And also we gave several numerical examples during the last lecture, and today we continue in this topic. So we have just a few slides before we started the parametric classification, which is one direct application of this estimation theory part. Okay. Here, if we have data, as we mentioned before, that if we have data like a series of data and we are interested in some hidden parameter, like you have some measurement, and this measurement like y1 equal to x plus n1, and y2 equal to x plus n2, and so on until yn equal to x plus nn. Okay, so we have n measurements, and we are looking for some hidden parameter x. And this x, as I said in the previous lecture, that sometimes we don't have any information about x, so for us it is uniform from -infinity to infinity. In that case, the maximum likelihood estimator would be, or will be, the optimal one, and we can solve this. We approve that x is the mean. If n is Gaussian distribution, then, or normal distribution, then x is the mean, and then we can find the mean. The maximum likelihood mean is just taking the summation of yi divided by n from I equal to 1 up to n, and this will be the estimation, the maximum likelihood estimator for x. But also we gave another example, that if we have some uncertainty, knowledge, or we have some impression about x. So x is not from -infinity to infinity for us. X, we have some information, like for example, x can be, in our information, is uniform from 1 to 2. In that case, this will not be, or this will not be anymore the optimal estimator. This will be suboptimal. The maximum likelihood will be suboptimal estimator in this case, and one optimal method is by using maximum a posteriori. And we explained also last lecture how to solve it. Whatever was the distribution of x, if our uncertainty of x is another Gaussian, or another normal like this one, and we have mu x, then also we explained how we can optimally find the average of x based on the observed measurements. This was explained last week. Now, if we add another assumption here, in this model, we assumed that those noise elements are independent. But what if they are correlated, if they are dependent? If they are dependent on each other, so this also will not be the optimal solution anymore. This will be also suboptimal, because now we have correlated noise or correlated measurements. In that case, we should go to the general form of the multivariate normal distribution, which is given in this this formula as we showed it before in, I think, in part 3. And here we have the covariance matrix of the noise, and here we have the inverse of it, and here we have y minus, actually this should be the mean of x. This should be the average. Okay, this is the general form, or x times 1, because now we have only this single x here, single element. In that case, we should subtract y vector from x all the time. So x times 1 here is one vector of 1s, as you can see it here. So we just apply the we take the logarithm as we showed before. This is the logarithm of the likelihood, because now we are trying to find the maximum likelihood estimator. So as we did last lecture, just we take the log of this function, but in previously, because we were assuming that the noise are independent, so we just multiplied all those likelihood distribution together. But now we don't multiply them together. Now we use this formula, and we have, when you take log for this function, then you will get this form, and you can see that we are interested in x, and x is only in this part. This part doesn't have any x, so we don't have any x, so we can differentiate with respect to x. So this will be 0, this will be 0, and we will have only this part. And in that case, the maximum likelihood estimator for x will be this formula. It is 1 transpose times the inverse of the covariance matrix of noise times the measurements vector y. This is just, I mentioned, if you have correlated measurements. However, most of our measurements, we assume that they are uncorrelated. But this is in case that you have some correlated measurements. And here in this example, what if you have uncorrelated measurement like this one? 3 situations. And here we have also uncorrelated, but 2 measurements with different variances. As you have smaller variance, it means that the measurement was like more accurate. And here, in case that we have like correlation, So we try to solve this if you have 2 measurements only. So you have like y1 and y2, okay, in 3 different cases. The first case, they are identical measurements in terms of variance, but they are independent. This is the first case. The second case, that they are independent, but one measurement is more accurate than the other. So if you have 2 measurements, for example, and one measurement is like, let's say, more accurate, like 5 times accurate than the second measurement, how can you combine them? One may say that, okay, I will take the more accurate measurement and just ignore the other one. This is not the optimal solution. The optimal solution is that even the less accurate measurement, it has some information that you should use. This is the concept of this part. And finally, we have completely like correlated measurements. And if you solve them, I solve them by hand. So you can just apply this formula. So the maximum likelihood estimator, the best estimator for x, should follow this equation. And now we have this R. So just I apply this R inverse in this case, because we have diagonal matrix here. So the inverse will be just like 1 divided by the diagonal elements. So in that case, in case that you have independent and identical measurements, the maximum likelihood estimator will be as expected, y1 plus y2 divided by 2. This is the same as this one, if they are identical and independent. In case that they are independent, but they are not identical, so they have different variance. Different variance means different accuracy. In that case, the optimal combination will be this formula. So you can see that you weight the summation of both measurements according to their accuracy. The more accurate one will receive higher weight. For example, if we assume the first measurement is more accurate than the other, what it means? More accurate means that the variance will be smaller. So if the variance sigma 1, 2 is very small, compared with sigma 2 square, what happened? This sigma 1 square will be much smaller than sigma 2 square, so you can ignore sigma 1 square, then sigma 2 square cancel sigma 2 square, then the optimal will be y1. Why we give more weight for y1? Because it has more accurate measurement, or more higher accuracy. Plus sigma 1 square divided by sigma 1 square plus sigma 2 square. So if sigma 1 square is very small, then we take less percentage for y2. So it is weighted sum between the measurements, and the weighting depends on the accuracy. This is the concept, the physical concept behind this. Okay, and finally, if we have correlated measurement, then also it will be weighted summation of two measurements, but now the weights depends also to the covariance between both measurements. So this is the optimal likelihood estimator. So the optimal likelihood, this one is not always optimal. This maximum likelihood is not always optimal. It is optimal only if we have identical independent like noise measurements. Otherwise, it becomes suboptimal solution. Okay. Another example, but I will not go through it, just to give you the concept of the example. If you have like big system, and this system will get failed if k of the subsystems fail. So the system has some like it is well known in reliability engineering. So we have like redundancy in the system in the way that if some of the system fail, the whole system will continue working or functioning. It is like in airplanes, for example. So in that case, we have some system, and we assume that the failure rate depends on the lambda for each subsystem is lambda, but the whole system will fail if k of the subsystems have failed to operate. Okay, and then the time of failure is given like xi. So xi is the time of failure for each subsystem. For x1 is the time when the first subsystem has failed, x2 is the time where the second subsystem has failed, and so on. So in that case, the whole system will fail if all the subsystems has failed. The k of those subsystems has failed. You can see that we assumed in this assumption that the time is computed like one after one. So there are some dependency. Okay. Now you have measurement. What the measurement that you have? You have only y. So you have the time when this subsystem has, the system has failed. So you have, for example, you have let's say y equal to 1 year. Another system failed after 3 years. Another system failed after 7 years. Another system failed after, let's say, 1 year again, and so on. So we have some vector of times where the system has failed. This problem can be expressed as a gamma distribution. This y is like a random variable, and it can be computed as if everyone is exponential distribution, then the distribution of y will be gamma distribution as it is given in this formula, where it depends on k, it is sometimes called the number of freedom, and also depends on lambda. So if you don't know, you have data, but you don't know k and you don't know lambda, how can we estimate k and lambda from the available data? So this is one thing that you shouldn't use, for example, normal distribution, because you know now we have gamma distribution, so it will be more accurate if we use different distributions. And we will see later how when we apply these concepts also in classification and in regression. So you can get more accurate results if you know the behavior and the physical behavior of your system. But we will skip this. Yes. Okay, now we come to the parametric classification, where we apply those concepts of estimation theory in classification. Okay, In classification, as we mentioned before, that we are looking for the probability that our attributes belongs to class Ci. So now we assume that we have like k classes. It can be like C1 or C2 or C3 or whatever. And what is the probability to be in class Ci based on the available attributes that we have? And as we explained this several times before, this could be expanded by using Bayesian formula to be in this form. So it is the distribution of x given Ci times the probability of Ci divided by the evidence is the distribution of x regardless of the class. Okay, and now we are looking for to maximize this. Usually we are looking to maximize the probability of Ci given x. So for example, if we have 3 classes and we have certain attributes x, and when we compute C1 given x, it gives, let's say, 0.3, and P of C2 given x, it gives us, for example, 0.6, and probability of C3 given x, it gives like 0.1 and so on. So if this is the maximum, then of course we should select this one. We should select this one as far as the risks are the same of selecting this class. We explained this before when we talked about risk management. So if the risks are similar by selecting this class, then we should select this class because it gives the maximum like posterior probability. Okay. Now we like to build a machine learning algorithm based on this formula. Okay. What we define now, we define what is known as discriminant function. What is the discriminant function? Is the upper term here. So it is f of x given Ci times b of Ci. Why? We know that every element here is positive, is always positive. It cannot be negative. It can be 0 or more, okay, for every element here, because they are representing probabilities, okay? And in order to maximize this one, you can see that this f of x is not depending on the class. So this will not have any effect in the selection, because this will be the same over every class, C1, C2, C3 until Cn. It is always the same, this value. So we can simply ignore it. Okay, now maximizing BCI given x is the same as maximizing the discriminant function. The discriminant function, we call it Ji at x, is f of x given Ci times probability of Ci. Again, because we have multiplication, and this distribution can be also a lot of many multiplication or product function, it is easier to deal with logarithm, as we explained last lecture. So then we take the log, but I named it the same, so I should use maybe hat or something, but it doesn't matter. So you know that we take the logarithm for this function. So it is log of f of x given Ci plus log of probability of Ci. Okay, now as we also explained before, this distribution could be estimated from the data that we have. We have data, so we can deduce this from data, and also we can estimate the probability of the class from data. In that case, what we need, because we have limited number of data, even you have like thousands of elements, they are limited. And in that case, we should use either maximum likelihood estimation to estimate this probability and this distribution, or we should use, for example, the maximum posterior or maximum likelihood, or whatever technique we should use in order to estimate. So this, you should it should be clear now why we started by estimation theory. We started by estimation theory because we need to estimate those elements in order to build this discriminator function or discriminant function, which will be used in machine learning. So we will use them a lot, actually, this in the practice as well. Okay. As usual, and as everyone, they always like start, or they assume normal distribution. Okay, normal distribution, as we explained also before, it can be many times justified. Can be justified in many applications that the data have are distributed according to normal way or normal distribution. However, as I said, in few cases, it might not work properly when you use the normal distribution, and especially if you can think about the behavior of the problem, that it follow gamma distribution or follow other distribution, then we will see how can we build discriminant function based on the new distribution. And in that case, you can get much better results in some situations. However, most of the packages available in the machine learning packages, they assume normal distribution, most of them. Of course, or some other famous distributions as well, but not like odd distributions. In odd distributions, if you are working like in data analysis or working in some company and you have some kind of odd distribution, most probably that you will not find them ready packages. You need to build it yourself. And this is what you can, we will see how to do it. Okay. Yes. Now, if in the beginning I will assume only single element, so you have only single attribute. You have single, like the price of the car, for example, and the class of the car, for example, or the income of the customer and his class. For example, if you are working in car selling company and you have many customers in your history, so based on the customer history that you have, assume that one of them is the monthly income of the customer, and then at what class car that customer usually sell or buy. Sorry. For example, you have class 1 of cars, maybe the cheap cars, class 2, and the class 3, and the class 4. So based on the monthly income of each customer, so you have some classification. Okay. Of course, in reality, we should have much more like attributes. But here we assume, because now we started with single attribute, so we assume that only single attribute, and later in this lecture, we will generalize it for the multiple attributes as well. It will be quite smooth generalization after that. Okay, now we have these measurements, and we assume that the distribution is normal. We take the logarithm for this part. When you take the logarithm, as I said, log of multiplication is summation of logs. Log of division is subtraction of logs. So 1 divided by square root of 2 pi, when you take the log, it gives this value, minus log sigma I, minus the logarithm of exponent. They cancel each other because they are like inverse functions to each other, and then it becomes minus x minus mu I square divided by 2 sigma I square, plus log of b, the probability of ci. Okay, now you can see that those are not function in x, so actually they will not have effect in selecting the maximum, because we compute ji for each class and then we select the maximum one. We select the maximum one. Okay, so if you know mu I in general and the probability of ci, then you have solved your problem. But if you don't have them, then you need to compute them from your historical data that you have, from your database. Okay, how to compute them from the database? We can use just the maximum likelihood, because we don't have any pre-knowledge about x, how it is distributed. So in that case, we can compute them from the data. So for example, the mean of we compute the mean for each class. We compute the mean for each class and the variance of each class. How to do that? I will do it on whiteboard, because in the slides maybe they are not so clear. And I will start with simple example about this x and the class y. Okay. Okay, let us talk about the salary and the class of the car, the same example. So now, if the salary is given here in €1,000 per month. So this guy, his salary is €2,000 per month, and usually the car that he bought, it belongs to class 1. That guy, another guy, that his salary is $5,000 per month, and he also bought from class 1. The third guy, maybe his salary, let's say, 3 and he likes cars, so he go to class 3. So he put all his salary for the car. And maybe this guy is, let's say his salary is 2.5, and then he go to C2, and this guy is just data that you have before, that maybe this one is 7,000 and he go to a class C2 and so on. Okay? So this is the data that we have. Now we assume that we have 3 classes only, and because this is our data. So we have 1, 2, 3, 4, 5. So we have only 5 measurements of 5 historical data. How could we compute MI and CI square out from this data? Okay. Now about M1, what is the average salary for those who buy car from class 1? How to compute it? First, determine in your data C1. So we have this C1 and this C1. Okay, let me add another one here. Maybe it will be more useful. So this guy, let's say his salary is also like 4,000 and he C1. Okay. So now we have three numbers. They both class C1. Okay. What is the mean now? The mean is 2 plus 5 plus 4 divided by what? Divided by 3, because we divide by the number in the same class. So we have class 1, class 2, class 1, class 1, and class 1. We have 3 items in class 1, so we divide by 3. This gives us average M1 for those, the average salary for those who belongs to class C1. So it will be 2 plus 5 is 7, plus 4 is 11. So it is 11 by 3. Okay. How to compute the mean M2? The mean M2 that we see how many guys in class 2 and their salary. So we have only one guy and his salary is 7. So the average is 7 divided by what? By 1.
2 guys.
Yes, so it is 2. So it is 7 plus 2.5 divided by 2. So here the average salary is 7. It will be 9.5 divided by 2. The average of the third class will be only 1 in the third class we have. So we have only 3 divided by 1. So the average is 3. Now we have vector of M1 and M2, M1 and M2 and M3. So this is the average for each class. How to compute the variance? The variance of each class, remember, this computation is maximum likelihood. We follow the maximum likelihood estimation to compute the mean. If we have some pre-knowledge about the mean, how it will be, then you should apply the maximum a posteriori, as we explained in the first part of this course, of this lecture. Okay, now we compute the variance of the first class. The variance of the first class equal to, I showed how to do it by hand, because when you implement it by software, you know what you are doing. Okay, now you take the mean. So the mean here is 11 divided by 3. Okay, and then you subtract the mean from x, from the salary. So it will be x, yeah. So it will be 2 minus 11 divided by 3 square. It is computation is the average of the variance plus, what is the second one? It is 5 minus the same 11 divided by 3 square, plus the third one is this one. So the salary is 4, so it is 4 minus 11 divided by 3 square, and divide by, if we are looking for the unbiased estimator, actually we should divide by the number minus 1. Okay, but usually in machine learning especially, we have a lot of data. Since we have a lot of data, usually we just divide by n. Doesn't matter. It doesn't matter. So we can divide by 3. But remember, in order to have unbiased estimator, you should divide by 2. Okay, this will be S1 square. Okay, now S2 square is the same. So we take the summation, but for C2 we have this salary. It is 2.5 minus the mean of C2 is 9.5 divided by 2 square, plus the second one is 7 minus 9.5 divided by 2 square divided by 2. Okay, and the third one as well, and this is the nice thing that we divide by n, because if divided by n minus 1, this will be 0 here, so it will be a problem, but we can divide here by just by 1. Okay, even some people, they say that the variance here can be 0 because we have only single element, but anyhow we need to compute. This will not be observed in reality because, as I said, we have a lot of data. Actually, if you have just small data, you will not be able to extract any useful or that much useful information. Actually, usually we should have large data in order the machine will be able to extract useful information. Okay, anyhow, this is the way how to compute S1 square, S2 square, S3 square, and M1 and M2 and M3. Where we substitute these elements, we substitute them here. Okay, so now you build your function, discriminant function, in this way. So J1 of x equal to, you can ignore, as I said, the first two elements because they are not functioning x. So it becomes like minus x minus. J1 is dependent on the mean mu1. So we computed already m1. Okay? Square divided by what? 2 s1 square. That we computed before. We computed before. Okay. I use S1. Why I didn't use sigma I square? Sigma I square is assumed to be the actual sigma that we don't know. We have just finite data where we estimated this M1 and S1 square. Then plus log of the probability of C1. How many elements that we had in C1? 3. And the data? 6 data. So it will be 3 divided by 6. Okay. Now, J2 of x equal to minus x minus M2 square divided by 2 S2 square plus log, how many elements that we have? 2. So it will be 2 divided by 6. And J3 of x equal to minus x minus M3 square divided by 2 S3 square plus log 1 divided by 6. Now you built your first machine learning algorithm based on the classification, parametric classification. So this is the first parametric classification that now we build. Now in your computer, you put these 3 functions, okay, in your computer. Now if you have a new customer, his salary, let's say, is 8,000 euro per month, and you are, as a seller man, you like to see in which area in your stock you will take this customer. You would like to estimate what is the class that the customer will buy the car. What you do, you substitute 8 in those 3 discriminant function, and you select the largest one. It's simple like that. So, for example, you substitute 8 here, and here, and here. Then you find what is the maximum, and the maximum is the machine what tells you that this guy will go to buy that product. And this could be also used for like artificial intelligence, like consultants, for example, or seller. That you know that when you open some websites, usually you receive some advertisement. It is artificial done, so there is artificial intelligence behind it. So they try to collect some information about you in order to direct the best advertisement for you that you are looking for. Of course, sometimes they use only keywords that you are searching about something, but also if they have more information about you, like where are you working and your salary, if they know those things, they can direct the best product for you that they are almost sure that you will buy it. Okay, so this is the way. This is the way that how to compute things from data. Of course, you will not do it by hand. Usually, there is a computer that you can compute those elements. All what is coming after that is is just based on the simple example that I solved it here. So it is important when you read this section to come back to the recorded lecture and try to understand this example well, because this example, even it is very simple, but it gives the main concepts, how to build the discriminant function and how to make the parametric classification of data. Here they said that what if you all of them, they have the same probability. It means that the data are, or the classes are evenly distributed. In that case, this probability is the same as this one, as the same as this one. So this one we can just ignore because they are the same. And what if all variance is also the same, or are the same? Then you can also ignore this one. At the end of the day, you will have only the mean, the impact of the mean. Only the mean will affect your discriminant function, and then you select the maximum one, which has the closest to the mean value. But this will be, of course, a special case. Okay. We have data in the model that we have one-dimensional data consists of 1,000 entry with only 2 classes. Okay, so I want you to download this data and also try to build this discriminant function for 2 classes. For example, you can take the first 500 elements of the data, try to make the classification, build your machine learning algorithm, and then try those 2 for the rest of 500 elements and try to validate if it works fine or not. Okay, no exercise. Actually, the same concept could be used for regression, but in the regression part, we have already studied the regression in details. However, starting from like a probabilistic approach, if we like to build a probabilistic approach for the regression, we will lead, or this will lead to the same formula that we had before in the second part of this course, but I will go fast about it. So here we have y equal to h of x plus n, and we are interested in x, and we don't know h, but we can also estimate h as j, for example. So we put some estimation, like we say that it is polynomial, and then we try to find the elements or the parameters of this polynomial. Now we have this joint distribution of y, the observation given the data x. We know that the joint distribution between x and y, it can be given expanded in this way. And finally, we can build the log likelihood function, like the log of the multiplications, because we assume the data are independent, and then it becomes the summation of the logs, as we know, in this way. So when you take if you assume that your data is exponential, is normal distributed, then finally you will reach to this formula, and we like to maximize the likelihood, which means that minimizing this function, and this actually exactly what we have done in the second part. So actually, in the second part, we minimized the mean square error. So the mean square error is the optimum if your noise is Gaussian or normal distributed and independent parameters or entries. Okay, so but we don't need to do it again, because we have already in part 2 studied this in details. Okay, in general, in the regression, for example, what you do, you have data. You take this data to the training part. So you divide your data into 2 parts, training and validation. You take the training part. You try to optimize the model parameters. For example, if it is linear, for example, parameter. Then you check the result with the validation portion of your data. Is the error acceptable? If yes, and you got that the result, of course, you might use the validation also to improve the data or the model. If no, then increase the model complexity, okay, and then optimize again for the data over training. Acceptable error. If yes and no, go back, and we continue until we got the learning process done. However, the question now, at what extent we can continue to increase the model complexity? Because if we increase the model complexity too much, then we might get what is known as overfitting or memorization instead of generalization, as we studied before. To study this part, so in general, that the error between the model result, this is your model, you assume that your model is j of x with a parameter, and this is the expected value of y given x. Okay, usually the error outcome from your estimation can be divided into two parts. Part is called due to the biasing. Biasing means that the difference between the real model and the assumed model. So we have bias and we have variance. Variance is due to noise. Due to the noise. Usually we can reduce the error due to the bias by improving the model. But for the variance you can do nothing, because the variance is due to noise. And noise, you cannot remove noise. Noise is completely random and unknown parameters. So this cannot be removed. What is our problem? Our problem here in the modeling, that we have the sum of them, but we don't know them individually. We don't know that this is due to the noise and this is due to the bias. Okay. And since we have here the total error or the total difference between the actual result, and we can know this through the validation, for example, process, and then we try to minimize this, but we don't know which one was the main source of this error. So we have some methods that we do, like this dividing the data into training and validation. However, if the training is a small number or the training data was not spanning the problem very well, then we have bad model. When we have bad model, we have high bias. Okay, and if we try to use more data in the training and we reduce the validation, maybe the amount of validation is not enough in order to see the real errors. So maybe just by luck that the validation was small and it gave very good error. Like the error was very small, but it was luck. It was not the actual situation. So when you take this to the real, like to solve real problems, you receive high errors. So actually, always we need to compromise between the training and the validation. And also we need to tune the model complexity. One method to tune the model complexity is using this equation. It is called augmented error function, instead of using only the error in data, because usually we use the error in data in order to improve the model. But now what they did, they add the error in data, but they add this one. This one is the model complexity. And they multiply the model complexity by lambda and the error in data by 1 minus lambda. Okay, now, if lambda equal to 0, what it means? Lambda equal to 0 means that we ignore completely the model complexity and we just concentrate on the error in data. So we like to minimize the error in data only. Okay, whatever was the complexity of our model. If you put lambda equal to 1, this will be 0 and this will be 1. So our purpose or our objective in this case is only to minimize the model complexity, and this of course will not work, because in that case you will get the model complexity maybe like linear if you started with linear, so the minimum is linear model. But how can you find the parameters if you don't have information about the error in data? So actually lambda should be greater than 0 and less than 1. Should be greater than 0 and less than 1 in order to compromise between the model complexity and the error in data. So this will be like penalty. You can see this part as penalty. So to minimize this one, you will need also to minimize the model complexity. So it is like a compromise between the model complexity and the error in data in order to reach to the generalization or to the right model, not overfitting or underfitting. Yes. So this is the way of the model selection procedure. There are some techniques in order to find the optimum or to compromise between the models, like using Bayesian, for example. They are used them also in order to find the optimal model. But we will skip it. Okay. We take a break for 15 minutes, and then we continue with the multivariate data. What if we have not single element? Because here we have single element, but usually in reality we have vector of attributes. We have x1, x2, x3 until x, for example, n, for example. And in that case, how can we build the discriminant function? Because actually with a single element, it is not useful with the single element. In reality, you don't. Most of the problem is that they are multivariate, not single element. For example, for that guy who would like to sell his car or the car from the market, so the customer usually that you have is not only his salary. It can be his age, for example. It affects, for example, his work, or male or female, and so on. So there are many parameters they should affect. So how can we build the discriminant function if we have multi elements or multi attributes? Okay, we have break 15 minutes and we continue. Okay, before we continue, I just would like to remind you that there is a quiz already now active in the model, and it will be the same. It is valid until Saturday. So you can start any time that you have. It will be 1 hour, isn't it, Rashid? 30 minutes now. Okay, you reduce the time. Okay, so it is 30 minutes quiz. So you can once you is it one time trial?
Yeah, one time.
Okay, so try to open it when you are ready to do it.
What kind? Is this mathematic like the last one, or
Is it method?
One calculation.
One calculation. Okay. And also about the report, you know that in order to get the credits of this course, we calculate the attendance as we check from sometimes, and also the report is one of the evaluation criteria is required, and the report requirements are already now in model as well. So you can check in model, so you can find the deadline is 15th of April, and you can work maximum 2 per report. So it is possible that 2 students work for the same report, or 1, of course. So and the deadline is 15th of April, and also no need for big issues here. So just simple idea, and use one of the machine learning algorithms either we gave in the course, or you using Python or whatever language that you like. You can use ready package, no problem. And try to have some real data. It will be better to have some real data that you can download it from the World, for example, Health Organization. They have a lot of data, or from some Finnish websites that they have also a lot of databases available, or you can collect some data from marketing or something. So it is good that you have some real data. But if you don't have real data and you want to design data, it is also possible, or use data that I loaded already in the model that you can also use. I gave also one task in the model that you can find it, that we have 20 recording for engines, for diesel engines, and out of those 20 we have 16 with a classification. It means that classification that about 8 or 9 they are good, and 8 or 7 they have some fault. And we have the time series, so you have some data that in time. And I want you as a task to try to build some machine learning in order to learn the relation between this time series and also the fault, if it is faulty machine or not. The last 4 measurements, they don't have result, so we don't know if they are faulty or not. So once you apply your machine learning to learn from the first 16, try to classify the last four to say that if they are faulty or not. You can use the same data actually as stock market data, for example, stock market measurements, and you want to classify stock market time realizations, for example. So it is also on model, so you can see them there. Okay. We continue. So here we have multivariate data. So we have X, like now you can see that we have X1, X2 until XD. So the dimension of the attributes is D. The dimension is D. So this is the elements, for example, the first customer parameters, the second customer parameters, until n customer parameters. So this kind of data usually you can find in like databases or historical data. It can be data from machines or from equipments or from bank customers or from supermarket customers or whatever. So we have a lot of this kind of data. Usually they are available in Excel files. Okay, and I will record one video how to read Excel files using Octave and how to extract data from them and how to save data as well with in Octave and MATLAB. In Python it is even easier. Okay. Okay, now we have multiple data. How can we deal, or how can we build the discriminant function if we have multiple data? When we have multiple data, then we have multivariate distribution, and we already see or saw before that the multivariate distribution, which is based on the we need to build the covariance matrix. And the covariance matrix is given by the expected value of x minus its mean times x minus the mean vector transpose. And it is given by the expected value of x times x transpose minus mu times mu transpose. And x is nothing but just vector of the parameters. And those parameters, not necessarily that all of them they are numeric. We might have also some like symbolic data like male and females, and as we will see today. So x can be, for example, if you have three attributes like x1, x2, x3, okay, and then for every x we have the mean vector. It is mu1, mu2, and mu3. Mu1 means that the mean of attribute 1, mu2 means the mean of attribute 2, and so on. For example, if x1 is salary, okay, and x2 is age, and x3, for example, is weight, okay, then mu1 means that the average salaries, and mu2 average age, and mu3 is the average weight. And here, when we say that x times xt, what it means, x usually is given as a vector. So it is x1, x2, x3, okay, times x transpose. Transpose, you take it, the transpose means that this way, x2, x3. So it is x and this is transpose. The multiplication here, it gives you a matrix. It will be like x1, x1. Of course, x1 is x1 square. This will be x1, x2, x1, x3 times x3. This will be x2 times x1, x2 square, and x2 times x3, and then x3 times x1, x3 times x2, and x3 square. Then you take the average of this one minus mu times mu transpose is the same. So it will give you like mu1 square, and this is mu1, mu2, mu1, mu3, and so on. So when you take the expected value of this, it gives you the covariance matrix R, XX, which can be defined like this one will be expected value of x1 square, okay, minus, when you take the expected value, it becomes expected value x1 square minus mu1 square. This actually is nothing but the variance sigma 1 square. The second one will be expected value of x1 times x2 minus mu1 times mu2. And this will be the covariance between x1 and x2 and so on. Yes. You don't need to do it by hand, of course. Everything will be done by computer, but we need to understand the concept behind it. The correlation between two attributes xi and xj is given by rho ij, and this will be sigma ij divided by sigma I times sigma j. And this, the correlation usually, it can be between like -1 to 1. Okay, so it is normalized. Okay, how could we compute them? As we did in the single case, in the single parameter, so we can compute m like summation of all attributes divided by n, and mi, the mean of every element, will be xi transpose divided, sorry, t is the number of the sample, over, we take the summation over t, divided by the number of samples that we have. I will explain them over some numerical example in order to understand how to compute them. And also, si square is computed in this way, and sij, when I does not equal to j, is given by the summation of xit minus mi times xjt minus mj. This is the maximum likelihood estimation of the parameters mean and the covariance. But remember, it is biased estimator. If we want to get the unbiased estimator, we should divide by n minus 1, as we said before. But when n is large, doesn't matter. Okay. Now let us try to build the covariance or the discriminant function for this case. So we have some data record from university about the students. We have 5 students here. We have the gender of the student, male and females. We have math scores and physics scores and biology. Okay. Now we can we will see how to compute the covariance matrix of this and the mean. Okay. The mean of every element is easy to find, because the mean here, the mean vector means that it contains mu1, mu2, and mu3. mu1 is the mean of the gender, mu2 is the mean of the math, mu3 is the mean of the physics, and mu4 is the mean of the biology scores. Okay, here we have some symbols that we have male and female, so we can give some numbers actually to differentiate them. This is one method that we can say, for example, female with +1 and male for -1, for example, or 0 and 1. So you can put some numbers in order to see how to compute them. Now we want to compute the mean of this data that we have. So what we have here, so we can, the first element is 1 or -1, and this, for example, if we say it is -1, so it is -1, and then 87 and 75 and 65. This is the first vector, plus the second vector. So you take the second element now. The second elements, it will be 1, 74, 63, 96 plus, and we add all of them, and then we divide over the number of data. So how many data that we have? We have 5 elements, so we divide by 5. So we take the summation and we divide all this by 5, then we get the vector of the means, the vector of the average of every element. And the covariance is computed in the same way that we did before. So for example, if you want to compute S1 square, you take the elements. S1 means that is related to the gender only. So you take every element and you subtract it from the average mu1. You take the square and you divide by number of 5. Take the summation and divide by 5. And the covariance, for example, if you would like to compute the covariance between math and physics, so in that case it will be S23. S23 is equal to summation, and you take every element here. So it is, for example, 87. It will be 87 minus what? Minus the mean, mu2, minus mu2, we did compute it, times the element is 75 minus it is mean, it is a mu3, okay, and the plus, of course you take plus, Now we take the second element. So this is the first one. The second one is 74 minus its mean times 63 minus its mean. So it will be 75 or 74 minus its mean, mu3, times 63 minus its mean, and so on. So we do that for all the data that we have. Then we divide by 5. Then we compute S23, and this one compute also S1 square and S, for example, 1, 2, and we compute every element here until we get the whole matrix. Until we get the whole matrix, that it will be in this shape. So we compute S11. I show it by, like for some elements, S12, S13, S14, and then S21, S22, S23, S24, and so on, until we construct the whole covariance matrix. And this will be the covariance matrix of this problem. Of course, we don't do that by hand. So in computer, it is only one command. In Octave or in Python, just one command. You put the data, you put COV, covariance, it gives you the matrix even if it is 1000 by 1000 elements. It is very easy to find by computer. But you should understand what is behind that, or how it works. Okay, now we build the covariance matrix, and this is the mean of the matrix, of the elements. Okay, and we can also compute the correlation matrix. And the correlation matrix, it gives you the relations between the elements. For example, here it shows that R13, one is related to the gender, and 3 related to the physics. And here it gives, for example, 0.84. It means that male is usually good in physics, for example. This gives the trend. But they are not good in, for example, in biology. So the trend is negative. So it gives you the trends of the between the elements. One of the problems when you deal with data that sometimes we don't have all data. So we have some missing of information from data. Usually we try to estimate the missing information if we cannot ignore it. Some data, they are important, or we don't have that much data that we need every single element of data. In that case, we do it as it is known as imputation. Imputation means that how to substitute missing data. Okay, but remember that not all data can be substituted. For example, if the missed data is some numbers from the like Visa card or MasterCard, some numbers are missing. You cannot just substitute them or estimate them, because they must be the same number. So you just put that it is missing information. Or if it is some numbers from phone number, so they are missing. So also you cannot substitute them. But in other kind of data, like we have measurements from certain sensors, and we have some sensors that measure, or some stock market. We have stock market prices, for example, and then we have some here the data are missing at some points. So maybe we can use some techniques in order to fit this data, like using regression, for example. We can use the data here and the data here, and then we can build some model in order to fill the missing data, or using Kalman filters, for example. Kalman filters is very useful in these situations. Okay. Yes. How to build classifiers based on this multivariate data. So now we have multiple data. Again, it will be exactly the same as we did in the single element. We take the logarithm. So, okay. So remember, this is Z here means that the covariance matrix, and this lines, the two lines, means that we take the determinant of this correlation or matrix. And you can see that both of them, they are not functioning X. So when we differentiate with X, or when we like to maximize this with X, we can simply ignore these first two elements. And we are looking only for these elements. Okay. Again, we can compute based on the class. We can compute them based on the class. And I will give also some numerical example, as I did in the first part in this lecture, to understand how to compute them. So if we stick with the same example of the car classes, so we have car class C1 and C1 and C2 and C3 and C1 and C2, for example, and C3. Okay, so those are the classes, and we have now not only the salary, we have some multiple like attributes. For example, here we have X1 and X2 and X3. It can be, for example, the salary, monthly salary. This one is age of customer, and this one is gender of customer, male or female, and maybe married or single, have children or not. So several kind of parameters. So what we have here, for example, the age, for the salary, for example, this guy is 5,000, his age is, let's say, 30, and male, and maybe he has family, so it is 1 if he has family, and if he has family with children, it becomes 2. If he's not married, then 0, for example. Then it becomes like 7,000, 45, and female, and 2, and so on. So we have data now. We have data, and we like to build the covariant, the discriminant function. You know that when you build the discriminant function, this is the learning. The learning now for your machine is by constructing the discriminant function. So now, when you have J1 of X for class 1, and J2 of X for class 2, and J3 for X for class 3. Okay. Now, once we build J1 and J2 and J3, we don't need this data anymore, because the data that you have, the historical data that you have in your computer about in that market, so they use the data, they fit the data into this discriminant function, and when now any new customer comes, then they compute J1, J2, J3, they select the maximum. It means that the machine itself knows that this customer, most likely, he will go, for example, to class 3 of cars, for example. Okay. Now, how to compute this? Again, it is exactly the same as we did before. For example, for C1, this is the C1. We compute the mean of the vector mean. Before we have single mean. Now we have vector of means, the average. So we have mean of the salary, mean of the age, mean of the gender, and mean of the marital status. So in that case, we have, for example, the mean of the salary, maybe it is 4,000, okay? The age is 48. The gender is maybe plus, let's say, 0.7. Means that most likely they are males in this category. If male is plus 1, and the marital status is like 1.2. So most of them, they are married, and both of them, they have children also. So all this mean, for example, this is mean for, what we mean by mu1 is that the average for class 1. The average of people of a class 1. Then we compute the average of people of a class 2. And the average of people of a class 3. So every time we will have 4 elements based on the data that we compute. How to compute them? Simply, this one plus this one plus this one divided by 3. Simple this way. For class 2, we take this one plus these elements divided by 2, because we have 2 classes and or 2 elements, and so on. Also, for each class, we compute this Z, or we can call them R. X is the covariance matrix. The covariance matrix is computed as we did just before, and it is given already here. In this slide, we call them S. We call them S. S both is the covariance for class I. So we have S1 and S2 and S3. Okay, so in this way, we computed the probability of each class is the number of the people in that class divided by the total number of n, and the average of each class, and the covariance matrix of each class. Once we compute those, we can easily build our discriminant function. This is the discriminant function, as we can see it here. So we just omitted this the 2 by and some elements where are not they don't have that effect on our decision. But now we kept here the elements like the determinant of SI, because the covariance matrix of each class, it has effect now. So we compute we can omit also this one if they are the same. If they are identical, then we can just ignore them. But now we have the element. So this is Ji of the element X. Now every new customer comes, we just substitute in this equation, then we select the highest discriminant value that we or the machine actually will suggest that this customer most likely will be belongs to that class. Okay. So we can do the same actually for the previous example of this example of scores and math, and this is some scores. And what I did here, simply I assumed that the class is the gender. So we have male or female. So those are the class. We have two classes, male or female. And based on that, we build the equations, the discriminant function based on that. So we build the discriminant function based for the males and the discriminant function for the females. Okay. Now our machine should be able that when we put for new entry, not here, but new entry, that one student got that the grade or that score in math, that score in physics, that score in biology. Machine tell us is he male or female. So it should be able to answer based on the historical data that you have. How much his answer is correct? Of course, it depends on how much this data, the availability of the data, and also maybe if you try for one, it gives you wrong answer. But usually we are interested on the average. For example, if it gave good answer or right answer in let's say 80% of cases, we say that this machine has learned quite well the relation between the scores and the gender, for example. Yes. We have one problem here that everyone working in machine learning, he might face it especially in the beginning. When we have a small number of data, and when the number of attributes are more than the number of data in certain class. For example, if you have, let's say, a 20 attribute, and one of the classes, they have only 5 entries. Okay, in that case, when you build the covariance matrix, your covariance matrix will be like a singular matrix. What is the meaning of singular matrix? It doesn't have inverse. So here you cannot build the inverse function for that. Sorry. You will not be able to build this SI inverse because it doesn't have inverse. And this is a problem. Okay? Or sometimes you have enough entries of data, but the singular matrix is not singular, or the covariance matrix is not singular, but it is ill-conditioned. Ill-conditioned means that when you take the inverse, the error will be very large, and sometimes even the determinant of this covariance matrix is negative. And we know that there is no log for negative number. There is, but it will be complex number. Okay, and this will be problem here. Okay, how to solve this problem? One method to solve this problem is by taking the average of the covariance. So what we do is, for example, if we have 3 classes, for the class 1 we have covariance S1, for class 2 we have covariance S2, for class 3 we have covariance S3. If we have one of those are singular or we have ill-conditional problem, then we build some S, general S, is equal to S1 times probability of class 1 plus times plus S2 times probability of class 2 plus S3 times probability of class 3. What is this? This means that we take the average of covariance. We average the covariance and then we use single covariance element as in this way instead of using covariance for every element. So we use single covariance. This, of course, will reduce the accuracy of our discriminant function, but still, at least, it works. Because sometimes it doesn't work if you use the singular or ill-conditioned matrices. Okay. Now we have some examples that you can download them from the model. I put this example in the model. It is already there. The file name is database2. It is Excel file. And here we have classes for health system. We have the income of people, the age, the weight, gender, and education level, health situation, and the height of every person. And then we have the classes of the health. So 10 means something, 9 means something, 8 means something. So it is related to the health, but every class means something in the health record. Okay, and we have actually 10,000 entry in the data, and we assumed 13 different classes from -2 till 10. And the requirement from here that we try to build this class. So what you need to do, you need to compute J1, J2 until J13, because we have 13 classes. And then when we have a new entry, you try to classify them based on this. Since you have 10,000 entry, you can take maybe 3,000-4,000 in order to build the discriminant functions and use the rest for validation, if your classification is correct or not. Actually, here I put also the code that I wrote, the code in Octave, which can perform this task. And I would record one video how to use this record as the same video that I recorded for the artificial neural networks, how to use it. And also I will record one video how to read files in Excel file, how to read them, and then how to use this application. You can modify this code, of course, for your report. For example, if you like, you have some data and you want Excel file and you want to use my code, here you can use it freely. You can just modify it a little bit to fit your application. Yes. This is just some explanation about about the code itself. Okay, that's all about today. So actually, today I can say that today we started use after the artificial networks about the other techniques, parametric machine learning. Today we can say that we started practically how to use some practical methods that you can use in your thesis or in your work. Any questions? Okay, thanks a lot.